been a relatively long day. We've had some pretty good brainstorming, some good formulation of questions, some good poses being posed from the audience. And so now it's time to kind of take stock a little bit and take a bit of a breather and prepare ourselves for tomorrow. And hopefully our next guest, I'm not trying to set you up.
All right.
I promise. Will give us some of that food for thought, because he's been directly involved in a host of planetary missions. Bob Ergen from the University of Colorado was brought forth to me as an organizer because I was looking to think about how this host of planetary missions that we've had over the last 5-10 years have inspired the planetary community to think about coupling of scales and to think about or to repose questions about those planetary atmospheres that they'd never thought of before, or they certainly didn't conceive before the mission. And so I think we're also in that boat. We're trying to jam square pegs into round holes at some point. Here's the things we think we know, but what are the unexpected things? We haven't really thought. I mean, thinking about the unexpected is something rather odd and maybe against scientific training. But I think maybe over the course of what we're going to hear about maybe some things that have sprung up that were unanticipated before and what science they've driven. So without further ado, thank you, Bob, for accepting the invitation to come into our community. And I'll offer the floor over to you.
Well, I want to first thank you for inviting me. All right, most of you don't know me. I deal a lot with, I've been on 8 missions actually, like most recently MMS, and I am on Solar Probe we've built on the electric field team. So I am very, very interested in solar physics right now. You'll see a couple slides from now that I know nothing about it. But I do know a little bit about magnetospheres. Jupiter and Earth in particular, where I've done some missions. And so I've been listening with interest in what you've been talking about a solar polar mission. And I was making a joke, since I'm probably going to be on the review panel because all of you will be conflicted. I will tell you it sounds very good at this point from my point of view and from my very naive point of view. So let me just tell you what the point of this talk is. The main point I want to get through, and part of it is that you need a complete picture. Part of it's really good for solar polar. You need a complete picture. That's what we have seen in magnetospheric community and Earth's in the Earth community, is that we had to get everything together to follow the energy flow, find out how the poles interact with the equator. So you could see how that would excite a solar polar mission. The other thing, though, the flip side of that is that we've gone into, let's just say at least at Earth, for most of our missions, what I call second-generation missions. In other words, we're no longer trying to get the big picture as much as we've identified the critical boundaries, and now we want to understand the critical processes, such as magnetic reconnection at the subsolar point, such as magnetic reconnection in a flare would be a great idea. So I think this combination has been a successful way forward. First, understand the big picture, find out where the critical regions are, and then attack the critical regions. And I've been hearing a lot of the same things. And mind you, just as an aside, I've been hearing a lot of the same conversations about how you make it sexy to the general public, et cetera, when we put together missions. Okay, so I would like to give 2 points through. One is we need the big picture, and 2, we need the complete model, and 2, we need to sweat the details a little bit. All right, so in a way, magnetospheric physics has had a complete opposite approach from solar physics, and not just because that's the way things are laid out in front of us. We have images of our poles. That's the only thing we can image. We have image envy otherwise. You now have polar image envy. We just don't have any images. So we've had to fight our way through making a magnetospheric model with a lot of in situ observations because we can't take pictures. So we started in the poles and we moved equatorwards. So it's a bit of an opposite approach, but nonetheless, we realized once we saw the aurora and we imaged it, that we needed to understand the equators to understand the aurora. And that was a very important finding. So I don't know how much everybody knows about Earth's magnetosphere, but so forgive me if I go back 50 years. But the first thing that we understood at Earth was that energy input, and this was a raging controversy at the time, but has come through the Dungy model, is basically that magnetic reconnection at the subsolar point opens up the Earth's magnetic field to the solar wind. So the Earth's primary driver is going to be energy from the sun, driven by the solar wind, and by opening up these field lines, not only can mass come in from the solar wind, can there be a mass exchange, there could also be an energy exchange. And that's the most important thing. We have subsolar reconnection, and then once again we have magnetotail reconnection at the Earth. And I think the point that I want to make on this is that magnetic reconnection, as important as a process as it is, I have seen so many people quote that, oh, it's the magnetic reconnection that accelerates all the ions that causes all this. It does not. The magnetic reconnection enables the acceleration. If you look at the amount of energy dissipated in a magnetic reconnection region at Earth, it's about a part in a million of all the energy that it frees up to be dissipated. And it's the same thing with a solar flare. I bet if you integrated what goes on in the reconnection site in the diffusion region, it would be tiny. And the process is highly processed after that. What it allows to happen is for energy input all along the flanks. Once you've opened it up, you're no longer closed. The energy can input. And this is a huge amount of energy. And what happens next is that after the magnetotail, the magnetic field builds up in the tail, it just builds up and builds up. It explosively releases itself into what we call substorms in Aurora. Now, doesn't that sound like a flare? Magnetic buildup, explosive release. And this is where, of course, we get the Aurora. But now we're going to go into, I'll just give you a little glance of what I call second generation. It took a lot of work for us to find out all the acceleration processes that are going on in the Aurora. And there are three of them that we've mentioned. And that's just because we're human beings and we like to categorize things. There could be, all sorts of subcategories of this. So you need to sweat the details after you get the big picture done. And so that's how, this is where we started, trying to understand the Aurora, and we ended up talking about magnetic reconnection at the subsolar points, looking at the equatorial magnetic reconnection in the tail. Maybe this argument can be made for a polar mission. So one of the advantages we have, though, I think, is that we have a relatively complete picture. I mean, relative to anybody, if we don't have a picture of the Earth's magnetosphere, what do we have? We've had more missions at Earth than anywhere else. Maybe not the sun, but at Earth. And so we really have got a lot of polar missions. Cluster 2 was in the polar orbit. Polar, well, by definition. We've had equatorial orbits, and these have really mapped out. We've visited almost every part of the magnetosphere, and most importantly, we've identified the boundaries and identified the regions where critical processes take place. Okay, so what about Jupiter? You're going to find that Jupiter's, when you look at the Aurora, at first glance, it looks exactly the same as Earth's, but Jupiter is not driven the same way, not at all. Jupiter is rotationally driven. First off, it's, if my colleague friend Bagenal was here, she would tell you, it is larger than the sun, the Jupiter's magnetosphere. It's the largest object in the solar system. Sun is small. Okay, forget about it. It rotates, though, very, very rapidly, 10 hours. And the second thing that happens at Jupiter that's very important, it has this moon, Io, that dumps about 1,000 kilograms a second, a ton of matter a second, which rapidly ionizes. So what happens is that the Jupiter is rotating the Keplerian orbit speed of Io is just a fraction of the Jupiter's rotation speed. So all that plasma that's dumped has to be picked up and energized into fast rotation. So the energy goes backwards in Jupiter. It doesn't come from the solar wind, like as in Earth, it comes from the solar wind into the Earth's magnetosphere. Here, it's coming from Jupiter's poles and accelerating the plasma that Io releases. So you would think, okay, this is a completely different driver than the Earth. It should be completely backwards, but then you look at it, and Jupiter's aurora are in the same place. They're in the poles. They look pretty much the same. They're precipitating electrons. There's a lot of the same physics going on in spite of the massively different drivers. Jupiter is very interesting, I find, because it has 3 types of aurora. This is called the main oval, for those of you who have not been familiar with this. And that is due to the co-rotation breakdown. There's a point in the magnet where the magnetic field can no longer keep the plasma that ton a second co-rotating, and that's out around 20 RJ, 20 Jupiter radii away. These are clearly satellite spots. Here's Io, here's Ganymede, here's Europa, and there's also what we call the polar aurora, which is the equivalent of what goes on at Earth. It's basically a more of a solar wind injected, possibly reconnection-driven aurora. But it is not the same. So many of the process, physics is the same, but the energy source is completely different. All right, so Jupiter is basically driven by this fact, by Io loading the equatorial region with mass. This mass has to work its way outwards, and it does through interchange instabilities and causes a large-scale current system that gives it the energy and the aurora. So Jupiter's also been relatively, well, not relative to Earth, but actually we have explored it fairly well. We had Galileo in the equatorial orbit, and now Juno is in a polar orbit. And we knew we needed the polar orbit for Jupiter. We really needed that to start understanding a lot of the processes going on, particularly for the dynamo people here. Jupiter's dynamo really was not understood. It has a massive magnetic anomaly in the north, and until we got satellites, Juno, into this polar orbit, we really couldn't understand fully how the dynamo works. Not that we understand it now, but we promise to be able to understand it maybe in 4 or 5 years. I mean, Juno's just gotten there. Give us a little time. Okay, so there's a lot of things you can do by having both the equatorial and the polar orbits in a magnetosphere of the sun. So from my point of view, the sun, well, it's probably driven mostly by turbulent convection, right? I mean, you have an near infinite energy source of really high density plasma stirring the magnetic fields. The amount of energy in that is just dwarfs anything in the corona. So you don't have a problem finding it. It's the problem is getting it from the solar surface, from the photosphere into the corona, more or less. So the energy flow is outwards, somewhat like Jupiter. It probably involves magnetic fields, whether it be a flare-like buoyant flux rope emerging, or in this case, maybe just simply small convection cells twisting magnetic fields. But it's the same process where we have an energy flow coming from the surface and going out. So to me, it has a lot of the same physics. It's got magnetic reconnection going on. It's got particle acceleration, and there's a lot of turbulence. And we can't dodge turbulence. None of us can. You can't in solar physics. You can't in magnetospheric physics. You can't in planetary science. It's pretty much of a universal process. But one of the things that is missing, clearly, is from the sun, in my view, and that's why this whole mission makes a lot of sense to me, is what about the poles? We've had Ulysses make a couple quick orbits. We have already, from these 2 orbits, 2 different plots of the solar wind speeds. at different phases of the solar cycle, I could think that this is really the area we need to cover. I'm excited, of course, about Solar Probe, even though it's equatorial, because that's going to give us our in situ measurements. So I think the whole basis of the fundamental basis that, oh, we need to get the poles, is actually making sense. As somebody from an outside, naive point of view, if you want the big picture, you want to complete your picture, I think we need the poles. So I could really support and advocate such a mission. Okay, but the second thing I want to talk about is the details, though. This is much more dear to my heart because I'm sort of a detail type of physicist. I go to all sorts of regions. I like magnetic reconnection, particle acceleration, and turbulence. Those are the physics I do. And so I don't care if it's at the sun. I think it's just as interesting at the sun as at Earth, as at Jupiter, as in a black hole accretion disk. I'm fine with all of that. So we've explored, this is what I call second generation science, because we've now explored and we found the hotspots at Earth and Jupiter. Now we have to go in planetary magnetospheres and try to find out what is driving these. For example, one of the biggest examples I'm going to use is magnetic reconnection. I mean, there isn't a solar talk. Probably none of you have ever been to a conference where reconnection hasn't been talked about like ad nauseum. So the question, this is a universal process. This actually sold an entire mission called MMS. Was the idea that it occurs in the lab in tokamaks. It occurs at Earth, of course. It occurs on the sun in solar flares. It occurs in, it's now believed to occur in gamma ray bursters as a conversion method of the electromagnetic energy from the jet creating the gamma rays. So there you have, one has, I could go on and on and on with the astrophysical examples, neutron stars, magnetars, etc., accretion disks in particular. So the idea basically is that we really need to understand that. It occurs from scale sizes ranging from centimeters, that would be solar, to to huge scale sizes. It also occurs from over 12 orders of magnitude in magnetic field strength. That's what I call a universal process. It doesn't take just this strength or this density or this perfect mixture. It just simply happens in a lot of places. And the other point is it occurs a lot faster than it should. In fact, in collisionless regimes, you get magnetic reconnection, such as at Earth, even though there is no resistivity, which is required initially, one would think, for this. Yet, so the physics is not terribly well understood, and that's why we ended up with the MMS mission. So magnetic reconnection, you've probably seen these diagrams. It's the basic idea is that you can annihilate or destroy magnetic energy. But again, I want to point out, it's not just the magnetic energy that's being converted to particle energy here. It's also all along the separatrix. It's not just the region, it's the entire length of the separatrix that has to be considered. So I will give you a little bit of MMS data, but not a whole lot because I got to keep the point here. So MMS was a mission, what I call second generation. We targeted universal processes when we sold this mission. We targeted things like magnetic reconnection, we targeted turbulence, we targeted acceleration, and we said that these are processes that occur everywhere. We visited most of the places on Earth. Now we need to really dig down and get the physics. The plan was basically to have 4 satellites and in a tetrahedron so that with spacing on the electron diffusion region size so that we could actually get answers. Now, I threw this slide in at the last minute because I heard about getting data down. Guess what? We had the same problem. We had about 100 times more data than we could possibly transmit. And we sold this with a kind of an interesting idea that we put these huge internal memories on each spacecraft. And so all 4 spacecraft are constantly measuring at their highest speed. There's no way we're getting this data down. Okay? But what we then do is send on thumbnails. So basically, here's an MMS orbit. We turn on the really high resolution where the reconnection regions are, but we are only going to transmit little bits of data down. So we send low resolution thumbnails down. They're a little bit more trickier than that, like magnetic field strengths, but it's like thumbnails. You're looking at them, you get a little bit interested. We say, hey, that could be a reconnection region. And then we will pick that time about that and transmit that down to Earth. Okay, so we still have to discard 97% of our data, all right, but we're still getting the high resolution physics down. Guess what? Solar Probe's field is going to do the same thing. We're going to take data the whole time as we come in for 24 hours, inside 30 RE to RS to outside 30 RS, and then we're going to take our time to try to figure out which data to send out, to transmit, because we can't possibly do it. So we call this the scientist in the loop system, because every orbit we had to have a scientist sit down, go through the thumbnails, and pick the times. We're automating it now, and believe me, this thing, I was part of the person that pushed this heavily. I got a lot of tomatoes thrown at me from NASA on this. But it turned out to be a great idea, because senior scientists love to do it. It gets people in the mission. It turned out to be a great training for graduate students. It turned out to be great training for postdocs. You can't imagine. We actually had people lined up trying to do this. It was fun. You get the joystick a whole mission. So I would think it would be a good idea if I just threw this slide in because I was listening to the conversation where people were saying, hey, how do we get all this data down? We have the same problems. Maybe this is a good idea to move on. In any case, I will say that MMS has moved on and has captured reconnection regions via this system. You probably have read a lot about going on. Maybe you haven't, but we actually have gotten absolute distribution functions and a lot of incredible data in the reconnection regions. So I'm going to tell you a little bit, not all the details on that, but what may be applicable to the sun. A few things that we've kind of tripped on that, since I've been reading a lot about solar physics because of Solar Probe, I thought maybe you'd be interested. One is that reconnection and turbulence are almost inseparable. And this is just from the magnetotail on Earth. This is the magnetic field that we're measuring. Occasionally we'll see blasts like this. Now, that is basic turbulence. The magnetic field is flipping and flopping. Now, you might think this isn't happening on the sun, but I bet you it is. I bet you will find regions like this. The electric field just lights up, the density goes low, and we get massive, this is electron energy, we get massively high energy electrons. Their temperature is less than 1 kilovolt, but we're seeing 100 kilovolt electrons coming out of here. So turbulence and reconnection are inseparable. This is actually a reconnection site right here between those two lines that is happening at this point. If you don't believe me, we've done a lot of study on the turbulence. We've looked at the Kolmogorov slopes and the dissipation regions, and when you average this up, it really matches a lot of other regions. This is time domain. This is a magnetic and electric field. It's hard to describe this in a quick hurry, but we have shown that this is truly looking like turbulence. When we look at detailed events, we could actually see certain types of waves and ripples developing. By the way, this is another magnetic reconnection region. Whenever you see this red line cross 0, that means that we have a possibility. But the point I'm making here is that reconnection and turbulence tend to be almost inseparable. Reconnection tends to generate turbulence. Okay, that's not the end of the story, though. So this is what we believe is going on. A lot of these reconnection regions are actually what we call surface wave or corrugated, like this. And what we're doing is flying through this surface wave, and you can see why you see density ripples and magnetic field ripples at the same time, and they're in the opposite sense. They're 180 degrees out of phase, which is telling us that it is not a compressional wave, but simply a surface that's wandering back and forth. So there's a lot of physics that we can learn. Now pay attention to this one. We also see electron scale reconnection. It just came out in a Nature paper a month ago. We talk about this a little bit, but we will see these huge, large amplitude parallel electric fields with J dot E being very, very large, meaning that there's conversion of electromagnetic, people call it dissipation, but it's conversion of electromagnetic energy into particle energy. Okay, so you're either heating it or accelerating it or doing something to the energy. So we see these events, and they're very, very microscale events. They're very, very small. So I'm going to give you a suggestion here, possibly nanoflares. Because this is essentially what would be going on in a nanoflare, is that you would be getting a small-scale, possibly electron-related reconnection event. These don't have ion jets necessarily associated with them. All the energy is being dumped into electrons at this point. We've made models of these things showing that they are, in fact, really sudden reconfigurations of the magnetic field. I don't know, this is a lot of Schindler stuff where you take the curl of E parallel, and you can calculate if there's been a magnetic field reconfiguration. It can be just a simple detwisting of a flux tube that is occurring. So if you do have, in fact, as I understand nanoflares, they're twisted up magnetic field, which then all of a sudden frees itself or detangles itself. So this is the type of thing that we're seeing, and that's why I thought you might be interested in this. And this was out of the Nature paper. The idea was that you get these little sparks, and they're also associated with turbulence again. But this time, it's the turbulence causing the reconnection. So do you see the loop here? Reconnection spawns a large region of turbulence. The turbulence then spawns small-scale magnetic reconnection. So we're seeing a lot of this occurring. All right, what about particle acceleration? I'm going to go back many, many years. The Aurora was our place when we wanted to look at particle acceleration. Clearly, we had strong electron acceleration coming down. I call the X-ray footprint of a flare the aurora of the sun, because that's where particles are being accelerated from a magnetic, due to the energy from a magnetic reconnection and lighting up an atmosphere. Just so you know that most of the we found at least 3 types of acceleration processes in the aurora, so it was not a simple process. And I know that people are saying, hey, what is it? What's going on? Well, there are lots of different processes. One, in the upward current region, the steady state aurora you're seeing, we see these large amplitude double layers that are just basically parallel electric fields, accelerating electrons downward. We call it the upward current region, but that means that's where the electrons go downward. Electrons are negatively charged. And so those observations are real, but we still don't understand the aurora because these double layers typically only carry 20% of the needed acceleration. Something else is going on. In the downward current region, that's the other way, where electrons are accelerated anti-earthward and don't have to fight a mirroring magnetic field. We see very, very active double layers. They live short, they move fast, they party hard, and they die early. And they keep reappearing all the time, and they're highly turbulent again. So this is a little bit different story. The other thing we see clearly is Alfvén wave acceleration. There's a huge part of the aurora that is almost entirely from Alfvén waves. In the spectra and the electrons look completely different. Instead of monoenergetic, they are broad energy, and they often have dispersion where you see the high energy electrons arrive prior to the low energy, meaning it's more impulsive than if you have an impulsive event, sort of like a solar type 3 radio burst, you end up with the high energy electrons coming out first. So we see a lot of these type events. And Alfvén wave acceleration is now a very, very hot topic in the aurora. We really want to understand it a lot better. Not surprisingly, Jupiter has a lot of the same acceleration. sources. The upward current region has Alfvén aurora and the downward current regions. This is some recent Juno data that show, in fact, the same inverted V that we see on Earth, meaning that the upward current region, probably at a huge, large double layer, is alive and well in Jupiter. Okay? However, Juno gave us a surprise. It really threw us for a loop. Everybody's thought that the co-rotation aurora is so steady, it just sits there, it's just happy, that it would be entirely double layers. But in fact, there's a massive amount of Alfvén waves associated with that, even though it appears to be steady state. So I think that was the surprise that Juno has given us. It tells you that you can't take anything for granted. We really have to understand this. But otherwise, we saw a lot of similarities in the acceleration processes at Juno, from Juno between Jupiter and Earth. Okay, so I'm not going to linger on too much anymore. I will tell you that the spots have been related purely to Alfvén wave acceleration. The satellites are really highly disturbing the local plasma, launching an Alfvén wave, and that causes the spot aurora on Jupiter. So when you say a footprint of a flare, is it from parallel electric fields? Is it from Alfvén waves? Probably from both. There's probably both in there. It's probably a much more complex process, and it's not just from the reconnection. It's processed, it's enabled by the reconnection, but it's highly processed at this point. So I like to talk about that in the sense that I think these accelerators, this is exactly right. It's the same physics, but these acceleration processes are going to be very, very difficult to reveal. Finally, I'd just like to say that I'm pushing for two things then. I'm pushing for the big, large-scale picture. I hope Solar Polar can achieve that. And I'm also saying that maybe we need to think out of the box in the solar community a little bit. I think Parker Solar Probe will show whether this is possible. Can we go after the details? Can we go after the universal physics that we really have to learn to understand the solar processes? So that's the point of it. That's all the wisdom I have. And thank you for letting me join you. I am a spy from the magnetospheric community, and I really enjoyed listening to your conversations today. Thank you.
Any questions or comments?
Sorry, I went overtime here. You're right. I mean, although we basically appealed to it through the saying that this was a universal process. I don't think we did a great job for the public, but I think we did a really good job selling it to our fellow scientists because we really stuck to the science. So I think rule number one is I would say stick to the science, one, and then try to figure out how to sell it. Okay? I think that would be backwards doing science. I understand your point. I mean, it's reality. We have to sell it.
How did you advertise?
We called them explosive interactions. We would show solar flares exploding. We would show things blowing up. And we would say, we're going to study this explosive process of magnetic reconnection. And at least we got all the people that liked explosions on our side. But again, I think really, I mean, in the early stages, we really sold hard that we were studying acceleration, turbulence, and reconnection. And that we went through all the places in astrophysics, all the fusion community. We got them involved. We tried to get a little bit of the solar community involved, but we were saying that, yes, this is good physics. So I think when I hear the work, I actually would recommend you stick to the physics first and then figure out how to sell it. If you need to put a camera on, yeah, that's good.
Oh, and then Michael.
Bob, I really like your classification of,
first generation and second generation missions. I mean, it's true. The magnetosphere community is MMS is a second generation mission focusing on these universal processes.
Yeah, we don't have any new places to go anymore.
But I mean, I think, the solar community is in that same boat these days with, the missions we're trying to fly, solar probe and solar orbiter, but, the poles is a new region. But I think, we got to perhaps not get hung up on trying to do everything on one mission. We should focus on what science we want to do, and perhaps that's a way to think about it.
Well, yeah, I agree. I think that from the discussions I've been listening to, it just sounds like, to me, I was immediately excited. I said, this is great. This is finally not taking more pictures of the equator and getting another, higher resolution of the granules. Measuring the magnetic fields, I like the idea of measuring BZ, for example, because that's a physical constant. You've got to attack certain things. And the dynamo idea sounded really interesting to me. Now, again, these are all my naive comments as a potential reviewer, as I keep trying to tell everybody, to these type of things. What? No, I'm not. I don't want to be the reviewer. but it often ends up the one person who's not involved in the mission ends up being the reviewer. So yeah, I agree with you, but I can't tell you that science. But stick to the science first. I've always lived that. I've been on 8 missions, and I've always stuck to the science, and that's been the winning formula. If it makes sense scientifically, then try to sell it.
You didn't talk about observations of impact of actually solar storms on a system like Jupiter or Saturn. That's one thing I would like to hear a comment on. And the second thing I would like to trigger is the whole context of these studies has become a lot bigger because we now know of 3,000 other planets. And the importance of magnetospheres in the evolution of those systems is coming about. So those two pieces I would like you to...
Absolutely. That's the science. When you think about, that's perfect. Those are great questions. Yeah, I'm sorry, I already went 10 minutes over. So the idea then is that I didn't talk, Jupiter is really relatively isolated from the sun. Okay, it's internally driven. You get very little relationship between what the heck the solar wind's doing and what Jupiter's doing. It's very internally driven. Earth, of course, is entirely dominated by the solar wind because that's where we're opened up. We have lots of magnetic storms. When IMF turns southward, we build up magnetic field and we get violent storms. Saturn, as far as I know now, I'm talking out of ignorance, is somewhere between Jupiter and Earth, and it's a raging debate whether it's more Dungy cycle driven or rotationally, because it has Enceladus, which of course releases plasma. So it's somewhat half Jupiter, half Earth. Now, as far as the exosolar planets, it's a very, very good idea. We need to understand what magnetospheres do, what they don't do, and we need to understand what the host sun of that planet does and doesn't do if we're going to talk about the evolution of life. And that is a really good way to show the relevance of the work that both of us are doing, that we all are doing. I'm now a solar physicist, though, because I'm on Solar Probe. So I think that yes, we need to really start selling that idea that not just the sun, but this is where we could learn the physical processes that go on in the sun, like flares. Dwarf M stars have a lot of flares. If we could understand what's driving those and understand how to analyze that and how much X-rays are coming from those, etc., then we could start understanding the host planets a little bit and how what would be required for those to survive and form life. And yes, so that's a very, very important part. Not just the practical part about, we always like to say the best thing that could happen to our field was that we have a giant solar storm right in the middle of the Super Bowl, right? And all the communication goes out. Everybody would fund us then. But in both of our fields, you know, all the solar and magnetospheric. So it would be wonderful to, you know, I mean, have both the practical point of view, but I think your point's on X. Did I miss something else you asked? I think you asked 3 questions, but I can't remember the third. Okay.
It's funny because the UK community has seen some funding ups. Okay, it's in the UK, so it's all relative. But they've seen some ups because of the 2012 Olympic Games for exactly what you surmise, right?
Yeah,
that
yeah.
They were worried about global telecom dropout. So they
during the
started
soccer.
during the Olympic Games.
Oh, during the
right?
Olympics, yeah. But if it happened during the World Cup, too.
Oh, that would be
problem.
catastrophic.
Yeah, I know. I mean,
Yeah.
you'd have a riot.
So, is anyone who's got another question for Bob? But I think you've given us a wonderful overview of your world
All
and
right.
things that we can tie to ours. And I wish you all the best of luck with your work with Probe.
Well, I wish you all the best with the solar polar. So that sounds very interesting, exciting to me.
So let's thank
Thank you,
Bob
everybody.
again. And I think everybody's kind of frazzled. So what I suggest is that we'll adjourn for the day. I believe the bus is scheduled to come after 5. But I believe that I'm hearing an undercurrent of participants may be interested in adjourning to Center Green 5, also known as the Boulder Brew Pub, for light refreshments. Thank you to all our afternoon speakers. You all done great. I'll look forward to seeing you all back here tomorrow for further discussions if I don't see you across the road in 15 minutes. Right, thank you. Bye.